We have all seen experiments in our childhood where we heat water inside a narrow glass tube, and as the water gets heated, it starts rising in the tube. I'm sure almost all of you have seen the operation of a mercury thermometer at least once in your life. But thermal expansion also has other consequences in our daily life which are not that obvious or apparent. For example, when we are laying out a floor from cement, we cannot lay the floor out in a single section. Often, what we have to do is we have to lay the floor out in identical squares, and each of these squares needs to have a small gap from the next square. Why do we do this? This seems to be too much trouble to go to lay a simple floor. The problem is not that great in regions where there is no large swing in temperature. But if you are living in a region where there are large variations in temperature, laying out the cement floor or the pavement of a road incorrectly can have major consequences. And we are going to understand why this happens in this particular session. Remember that all materials will display some expansion as we heat them. So, if we are heating a material through a particular change in temperature, we can say that change in temperature is delta T equal to T final minus T initial. So, this is the change in temperature undergone by the material. Now, if you have equal amounts of material of the same shape, you will notice that usually for the same change in temperature, the expansions of these materials are not uniform. For example, if we have a rod made from Pyrex glass, which is a special type of glass used for dealing with hot materials like soup or for baking, and we take another rod that is made from copper. So here we have a rod made from copper, and we have another material which is made from, let's say, invar. So here is a material called invar. Invar is a special alloy made from different metals mixed together. If we were to heat them through the same change in temperature, let's say that all three of these materials started out at a temperature of 30 degrees and we have heated them all to a temperature of 100 degrees. So this is our T final and this is our T initial. So delta T comes out to be 100 minus 30, that is 70 degrees Celsius. This is the change in temperature for all three of these materials. We would notice that they do not expand by the same amount. You would notice that copper expands much more in length and volume compared to, say, Pyrex glass. Pyrex glass will not show any significant expansion. The reason for this is the three materials in question have different coefficients for expansion, and that is what we are going to discuss in this particular lesson. So, we have three types of coefficients of thermal expansion. We have the linear coefficient of expansion, we have the area coefficient of expansion, and we have the volume coefficient of expansion. The area coefficient is also known by a different name. We also call it the superficial coefficient of expansion. The linear coefficient for expansion is given by the symbol alpha. The superficial or area coefficient is given by the symbol beta, and the volume expansion coefficient is given by the symbol gamma. So, we have the three symbols we require. How do we use this to determine what will happen to a material when it undergoes a change in temperature? So, these coefficients were discovered by taking identical slabs of material and allowing them to expand or contract through a predetermined range of temperature. We can see that if we take the change in length for a given object for a given change in temperature and divided by the original length of that object, it is equal to alpha times delta T, where delta T is the change in temperature, delta L is the change in the length of the given object, and L is the original length. Similar ideas carry over to area and volume expansion. So, if we take the change in area for a given object and divided by the original area of the object at the initial temperature, this will be equal to the superficial coefficient, that is beta, of expansion multiplied by the change in temperature. In a similar way, if we take the change in volume for a given material divided by the original volume, this is equal to gamma, that is the volume coefficient of expansion multiplied by the change in temperature, that is delta T. Depending on the values of alpha, beta and gamma, different materials will expand or contract to different extents. Please remember, a material that expands more on being heated will also contract more when cooled, and conversely, a material which has a low coefficient of expansion will contract less when cooled and also expand less when heated. We can also show that beta is twice of alpha and that gamma is equal to thrice of alpha. So if we know the value of alpha, if we know the value of linear coefficient of expansion for a given material, we can easily deduce the values of beta and gamma for that particular material. Now, you could ask what is the dimension or what are the units for this particular coefficient, the coefficient of thermal expansion. Well, if we carefully look at any of these formulae, for example, if we look at the formula for linear expansion, that is delta L divided by L is equal to alpha multiplied by delta T. On the LHS of this equation, we have delta L by L. So, a change in length is being divided by another length, which means that the dimension length is being divided by, again, dimension length. So, this comes out to be a dimensionless ratio. So, here we have a dimensionless ratio. It stands to reason that if the LHS is a dimensionless ratio, then the RHS also has to be dimensionless. So, in that case, if alpha multiplied by delta T is dimensionless, then the dimensions or unit of alpha has to be 1 upon delta T, or it is the inverse of the temperature. So, the value of alpha can be measured in inverse Celsius, or we can do it in inverse Kelvin, or we can do it in inverse Fahrenheit, whatever temperature scale is appropriate for your particular application. We can also see that since we can determine the values of volume and superficial coefficient of expansion from the linear value, we just require the linear value to make these other assessments. For example, let's take the material Pyrex that we have seen before. Pyrex is a special type of glass which has a very low coefficient of linear expansion. In fact, it is equal to approximately 1 times 10 to the power negative 5 in its magnitude. So, this is a very low value of linear expansion. So, if this is the value of alpha, then beta, that is the superficial expansion coefficient, will be equal to 2 times alpha, that is 2 multiplied by 10 to the power negative 5 in magnitude, and gamma will also be equal to 3 times alpha, that is 3 multiplied by 10 to the power negative 5 in magnitude. Other materials can have much higher coefficients of expansion. For example, metals tend to have a higher coefficient of expansion compared with non-metals. Now, coming back to the original question, why is it necessary to create gaps when we are laying out a cement floor? What will happen if we try to create the entire cement floor in one piece? The problem is that as there are changes in temperature, the cement floor will try to expand and contract based on increases and decreases in temperature. As the cement tries to expand, it will be stressed because it is pushing out against the boundaries of the room where the cement floor has been placed. If the stress becomes high enough, if there is not sufficient clearance between the cement flooring and the walls, the expansion will cause the floor to bend inwards or outwards and even break apart. This effect becomes even more prominent when we look at pavements which have not been designed properly. In regions when there are large seasonal changes in temperature, you will notice that the cement blocks on these pavements can break, sometimes without any warning. So this is an example where engineers and designers have to consider the expansion behavior of matter in order to create structures which can last a long time.
Manorama Horizon, learning made simple.